anything else that is important. So in this one, you're going to find as many patterns as you can. Use one or more patterns to help you complete the table. Be prepared to explain the reason. So like if you want the directions, I would just put find as many patterns as you can. Right, and then I'll let you. All right, so go ahead and do that. I'll give you some minutes. All right, who can raise their hand and share a pattern that they either found or that they heard? So you could steal a pattern that someone else had in their group. Daniel? The decimal each time divides by 2. So 0.5 divided by 2 gives me 0.25. 0.25 divided by 2 gives me 0.125. All right, any others? Caitlin? The denominator of the fraction multiplies by 2. So here, let me make a list. So decimals divide by 2. And then denominator of fraction times by 2. All right, any others? Gloria? So every time you divide the numerator by the denominator, you get the decimal that's down here. Okay, I didn't know that one. That's again. So dividing, and I'm just gonna abbreviate, numerator by denominator gives alphabet. So then, class, what would go down here? 0.0625. Okay. And then in this one, what is it? 0.0 what? Okay. I'll check in my book. This is the first time I'm doing it today, but oh, 5 at the end. Okay. So let's see. Those are the decimals. Good. Any other patterns that we notice? All right. So good observation. I know for me, it's hard to figure out what the pattern is. And there are ways to figure it out. So say we're just looking at, I mean, we have like, I guess you could say an input and an output. Say I'm just looking at one of the sequences. So like this one. A way that you could figure out the pattern, we'll first see if you're adding or subtracting to get that answer. Doesn't really look like it in this one. So then maybe I would try to see if they're multiplying, or you could say dividing by something to get the next one. So take one of the terms, 1/4, and then divide it by its previous term, 1/2. And then of course, I know you probably don't like fractions, but you can use Desmos to do the fractions that you don't want to work out yourself. So Desmos, anytime you put a fraction in, put the fraction in parentheses, 1/4 divided by 1/2, I get 0.5. Now that gives me what we call a common ratio. So if the pattern is multiplying, or you could even say dividing, by something each time, this is how you can figure out what exactly they're doing. But that common ratio or common factor is what you multiply by each time. So then when I take that 1/4 and I times it by the 0.5, I get 1/8. And of course, you can click this fraction to decimal button and go back and forth. You see that? So I agree, patterns are sometimes hard to figure out, especially when they're fractions or decimals, but that's how you can figure them out. And then see if it continues throughout the rest of the pattern. Oops, that's not what I wanted. All right, see, keeps giving me the next one. So try that with the bottom sequence. So I'll highlight it a different color. And maybe some of you already know what the common ratio is, but do what I told you. To find the common ratio, divide each number by its previous number, and that'll give it to you. Yes. And actually, I'll type in this definition because I want you to use it. All right, so find the common ratio and also write down this definition. All right, so common ratio, sometimes called common factor, so you might hear both, is found by dividing each term by its previous term. So then what's the common ratio of the yellow sequence? 0.5 also. So 0.25 divided by 0.5 does give me 0.5 or 1/2. And that's what I'm multiplying by each time to get the next number you'll see. All right. So it is possible to multiply by a number and the number becomes smaller. So questions on that? All right. So make sure we have that definition for common ratio down. I'll give you like 10 more seconds to finish writing and I'll move on. This activity, again, I wouldn't write every single thing down. I'll give you tips on what to write down, but try to see like if you can figure it out yourself. So the value of some cell phones changes exponentially after initial release. Here are graphs showing the depreciation of two phones 1, 2, and 3 years after they were released. So what does that word depreciation mean? What was that? It's going down. And that makes sense, right? Is your iPhone worth as much as like when you bought it? No. So there's always like a new thing coming out. So I would probably write that down in my notes, that depreciation means decrease. So whenever you see that in this unit, think decreasing, think growth or decay. Decay. All right, I'll start with a D, so that's kind of a good indicator. So then, looking at the graphs, and feel free, I guess you could sketch it. Maybe I'll blow up the graph and make it a little bit bigger so you can see. But it says, which phone is more expensive to buy when it first released? How does the value of each phone change with every passing year? So within your groups, figure out the answers to 1 and 2. And for me, taking notes, I wouldn't necessarily write down the whole question. I would rephrase it as, maybe leave some space. Phone blank is more expensive to buy when it's first released. So maybe like draw a picture. Like rephrase the question as an answer so you don't have to write like 2 different things each time. Right, so I'll give you 2 minutes to figure out 1 and 2 within your groups. I'm going to try and make those a little bigger. All right. If you dress up for Spirit Week, you can pick the reporter in your group. If no one in your group dressed up for Spirit Week, it'll just be whoever's standing, or not standing, sitting closest to where I'm currently standing. All right, so figure that out real quick. So table 2, which phone is more expensive to buy when it is first released? Phone B, phone A. What tells us that, class? Daniel? Okay, good. So in other words, towards the y-intercept usually tells you your starting amount. Compare them. This one costs $1,000 according to the graph. This is the value at when time is 0. This is the value when time is 0, 840. So yeah, phone A is more expensive to buy when it is first released. How does the value of each phone change with every passing year? So table 3, can you tell me how phone A changes each year? So is it by 400 every year? No. So it's different year to year. So we could say in year 1, and then in year 1, you could say that it decreased 400. In year 2, how much did it decrease? 240. In year 3, it decreased by how much? I haven't done the math yet. So you guys have it.
Yeah, 104.
104?
40.
It doesn't sound right. 140 what? Okay, that sounds more right. Okay, I heard 140. So yeah, that sounds a little bit better. What's this called in math terms? We've talked about it before. Well, it's definitely nonlinear, yes. But when I figure out basically how it's changing between certain times, that's my average rate of change, yes. And it depends on where you're looking. So if I'm looking from year 0 to year 1, my average rate of change is minus 400. If I'm looking from year 2 to 3, it's minus 240. So even though we didn't necessarily plug it into the formula, it would give us the same answer. And I did see a lot of average rate of change on your unit test, by the way. So I'm still making one of them x1, y1, the other x2, y2, and plugging it in. So like if I labeled it like this, I have 600 minus 1,000 over 1 minus 0. What's 600 minus 1,000? A negative 400. And then what's 1 minus 0? 1. Which isn't that what we got? Yes. So good. Phone B, how would you describe that? Table 4. What's the difference from year 0 to year 1? Good. So from here to here, it decreases 310, so minus. And then table 5, what about from year 1 to 2? What's the difference? For time purposes, does someone else have the answer? Daniel? Negative 157.5. So everyone know how we're finding this, by the way? So take the previous year minus it, the current year, that gives you your difference from year to year. So then for the last one, someone find that one. Okay, let me just verify. Did you say 118.12? Yeah. Okay, good. And keep in mind, That's from year to year. That's the average rate of change. It is possible that they could ask you what's the average rate of change from year 0 to year 2, or from year 0 to year 3. And that's when you would have to take note of what coordinates those are and then plug them into that formula. All right, but from year to year, those are our average rates of changes. Good. I know I didn't have you guys discuss these, but let's just kind of keep it moving. So which one is falling in value more quickly? Raise your hand if you think it's phone A. Raise your hand if you think it's phone B. All right, what's something we can look at to see which one's falling more quickly? Gavin?
The last few numbers, the last numbers on both ends.
Okay, so looking at like from year 2 to year 3, things like that. Something you can look at. Daniel?
Yeah.
The average rate of change, I guess you could say overall. You could calculate it from year 0 to 3 and compare. Also, which one is more steep? They do look pretty similar, but it does look like phone A is a little more steep. So visually, you might be able to tell. To know for sure, you might have to do it mathematically. So I would put in my notes, to see which one is falling in value more quickly, I would say calculate average rate of change overall. If the phones continue to depreciate by the same factor each year, what will the value of each phone be 4 years after its initial release? So according to that question, it's decreasing by a certain factor. How can you figure out what that factor is? Think about what we did in the warm-up. So common ratio, another word for it that the curriculum likes to use a lot, is common factor. All right, it's found by dividing each term by its previous term. So then if I'm looking at it for phone A, take one of the terms and we could say like our average rate of change, or we could take what's actually in the sequence. Let's do that instead. So 600 divided by its previous term, which was 1,000, what's that value? All right, thank you, it is 0.6. See if that pattern continues. So now take 360, so I'm taking what's actually in the sequence, like what my actual output was, and dividing it by the previous output, so by 600. Does that also give me 0.6? So yeah, it is decreasing by a certain factor, even though it might not necessarily look like it. And that certain factor is 0.6. So then if I wanted to keep the pattern going to figure out for year 4, I would take what number? $216, that's my output at year 3. And I would do what to it? Multiply it by 0.6. That'll give me the next value in the sequence. So that times 216 is right, so do practice the calculations. It'll help you remember it more. I don't use the past now, okay? Right. All right, 216 times 0.6 is good. And if we're making it look like money, I'll just add a 0 at the end. So phone A, 4 years after its release, is 129.60. Do that for phone B. Now, I don't know what phone B is decreasing by, but I did tell you how to figure it out. So do that. Try to figure out the common factor and then try to continue the pattern. I'll give you about a minute for that. All right, table 6, did we find the common ratio that phone B is decreasing by? What'd you get? 0.75. Anyone get something different than that? All right, so let's see. Take one of the terms. So I'll take 630 and divide it by its previous term, 840. Throw that in your calculator. Do we get 0.75? Yes. And if you're using the fraction, that's fine too. 3/4. Sure. Times it by 3/4 every time, and you'll get the next term. So then if I want to find year 4, what number do I take? That's actually my rate of change, so I might not want to take that one. Good. 354.38, and we're timesing it by what? 0.75. So think of it like a table. Coordinates could all be placed into tables if that's easier for you. So like for phone B, it goes 0, 1, 2, 3, and then we're solving for 4. And then my outputs are my Y values. The rate of change helps us answer different types of problems, like which one is decreasing at a faster rate. So sorry if that was confusing, but we're looking at the outputs, the Y values on our coordinates. So then that is what we are multiplying by the 0.75 each time to get the next number. So when I do that, what does my year 4 value become approximately?
6.5.
Okay, and then since we're talking about money, round it to 2 decimal spots, it would be 0.7. Yes, approximately. So then, which one is worth more after 4 years? Phone B, because phone A is decreasing at a faster rate. So yeah, phone B will end up being worth more. For each cell phone, write an equation that relates the value of the phone in dollars to the year since it's released, and it gives you some variables that it wants to use. E will be for the value of phone A, and W will be for the value of phone B. So I'm going to have V equals and W equals. We're going to make an equation for that question. Yes. So then to kind of remind you, there are some formulas that I gave you to help you with these exponential functions. There's one for growth and there's one for decay. What does the one for decay look like? If you can remember it, like pull it out of your memory, that's better than referring to it. So I heard 1 minus R, and then, sorry, what was before that? A. Anything else? Good. And then it's usually equal to Y, or in other words, like your output. All right. I won't be providing these formulas. That's FYI. You do have to remember them. But hopefully, like all these examples we're doing kind of help you with that, making the equation yourself. A stands for what? Initial value. Good. Initial value, or since it's an A, I always think of it as a noun. But whatever helps you. So what's my initial value of phone A? So that's what I'll put for phone A. For phone B, what's my initial value? Good. and then keep it going with this. Now, it's 1 minus R, which is for what? Good. Now, this can also be confusing. Or maybe not. Maybe it's not. Decay rate is what it's decreasing by. So if we're timesing it, say like for phone B by 0.75 each time, what is it decreasing by? It's decreasing by 0.25. And I know like that's hard to figure out, but the reason why we're timesing it by 0.75 is because we've already subtracted it from the 1, or subtracted the decay rate from the 1. So when you already know what you're multiplying by each time, just keep it like that. So like for phone B, 840 was times by 0.75. You wouldn't do 1 minus the 0.75 because it's already like subtracted. So this parentheses is already worked out. Does that make sense? All right, maybe not, but you'll see the pattern hopefully throughout the unit. So what you're timesing by each time, or in other words, your common ratio goes here to the t power or to the x power. Because that can change from year to year. Make sense? And it wants us to use t. So I'll actually put it there. So then for phone A, what were we multiplying by each time for phone A? So that is what will go in the parentheses. Well, 0.4 is what we were decreasing by. So if we wanted it to look like this, I guess we could write 1 minus the 0.4, and that's how they're getting the 0.6. All right, but since we already know what they're multiplying by each time, the common ratio, we can kind of jump to that now. All right, and that's how we make the equation. Any questions on that? So your starting amount times your common ratio to the t power, t being for time, since how much you have will change depending on what time you look at. All right, good. Any questions? All right, we're almost done. We have a card sort, or we actually made it into a booklet to kind of help you. Or to kind of save us some time too, because card sorts can be very time consuming. So you can use your phone, you could use your Chromebook, since you're probably going to need it anyway for the practice, whatever is quicker for you. And the card sort really only has a few questions. Right, so we're doing a booklet or booklet in place of the card sort. It is in the slides if you ever want to look at it again, or do it at home if you're absent. All right, so it was only 4 questions, just so you know. It was repeating the same 4 questions, but either way, like, you could probably tell the difference between growth or decay easily. So, and then it was just choosing between 2 options. So listen, for this one, growth or decay? Decay. So it's definitely not going to be the yellow one because it's not doubling, it's not increasing. Could be blue, definitely not green because it's not tripling, increasing. And then losing would also be decreasing. So really it's between these 2. To tell how much, well, take the y value, divide it by its previous y value approximately, and whether it's closer to 1/4 or 2/5, so 0.25 or 0.4, is how you can figure that out for sure. All right, so that's what you were supposed to be trying to connect. Would this one be growth or decay? Growth. And notice it's the same situations as before. So it's either doubling or tripling. To know for sure, take one of the y values, divide it by its previous y value. Whether it's close to 2 or 3, so doubling or tripling, is how you know for sure. And these are in the slides if you want to play it again for practice, but that's how you were supposed to figure it out. Good, any questions? All right, I prefer you not to sit around and wait for the bell to ring. I prefer you at least open up your practice and try out a couple, or maybe ask questions if you have questions. But yeah, that is lesson 6.